Hello grade 11 students. Today I am here to teach you mathematics relevant to your textbook. So what is the first topic that you have in your textbook? That's called real numbers. So here we use the letter R. So here we use another one line instead of R for real numbers. So actually this is a Greek letter. So we know every day we use real numbers. In A-level class, you will learn about complex numbers which are not real. As children, you always know what are counting numbers. What are counting numbers? In small classes, you did 1, 2, 3. So here, we'll first take counting numbers. So what's the set of counting numbers? We can write down 1, 2, 3, 4 and we can put 3 dots to represent that's continuing. But now we use another name for counting numbers. What are those? We call these are natural numbers. So you get the same set of numbers as counting numbers. What's the symbol we can use? We use N letter for natural number and here another line we put. Now when you take all natural numbers, there are so many types of numbers. We know about odd numbers. What are odd numbers? The numbers that are not divisible by 2. So if you want to write down the set of odd numbers, we can start from 1, 3, 5, 7 and it's continuing. Then what about even numbers? Even, that means numbers that are divisible by 2. So what are those? You can write 2, 4, 6, 8 and it's continuing. Then what about multiples of 3? That means starting from 3 times 1, 3, 6, 9, 3 times 4, 12, 15 like that. If I say multiples of 5, how can I write? I can write, what are multiples of 5? 5, 10, 15, 20. Triangular numbers. What are triangular numbers? So triangular numbers are numbers which makes triangles. So here if I take 1, then I can make a triangle with 3 dots. What about the next one? I can draw with 6 dots. Again I can draw with this number of dots. So how many numbers are there? So starting with 1, I can write starting with 1. The next number is 3. What's the next triangular number? 1, 2, 3, 4, 5, 6. What's the other one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here these are called triangular numbers. The numbers we can make triangles. Then what are square numbers? Square numbers that we can make squares. So here starting from 1, What's the other square number? I can draw another square with 4 dots. What about the next one? I can draw with 9 dots. What's the other square number? 4 dots per row. That's 16 dots. So here 1, 4, 9, 16. We call those are square numbers. Then what about prime numbers? So prime numbers are only divisible by 1 and itself. So what's the lowest prime number? 1? That's wrong. Starting with 2. So the lowest prime number is 2. 3, 5, 7, so on. Then the numbers which are not prime, what do you call that? Composite numbers. So here, what are the other numbers which are not prime? 1, 4, 6 like that. But you need to remember composite numbers means there are at least 2 factors. So when you take 1, only 1 factor is there. So 1 is not a prime nor composite. So remember that. So we can't take 1. We can start with 4. 5 is there. 6 is not there. 7, 8 like that. And I'll write another number here 7 and the other one is 11. So here 8, 9, 10 all are composite numbers. So you know now several natural numbers: even, odd, square, triangular, prime and composite. Then we need to know when you take all these whole numbers, we call another set as integers. So you need to know what are integers. So integers, we take only whole numbers. It can be negative or positive. So what's the symbol we can use? We use letter Z for, and we write another line there, Z for integers. So what are the integer values? We can write the set. It can be any negative value. So I can start with -3, -2, -1 and 0 also an integer. We can take 0 also as an integer. 1, 2, 3, so on. Now again, when you take integers, you can divide into 2 parts. Negative values separately and positive values separately. So what you call the negative values? Negative integers. What you call the positive one? Positive integers. So here I can use 2 sets again from integers. Positive integers. So what's the symbol? We use Z plus. And the other one we call negative integers. So what you call that? Z minus. So we can write down the set as Z plus is 1, 2, 3, so on. And what about negative? Negative I can write starting from -1, -2, -3, so on. Here, when you take integers, without writing this part, I can write something like this also. Z is equal to, starting from 0, plus or minus 1, plus or minus 2, plus or minus 3. This is also another way of writing integers. So you need to remember all these symbols and types of numbers. So integers we use letter Z, natural numbers we use letter N, and real numbers we use letter R. Now we'll take what are rational numbers. So rational numbers are defined as if we can write any number in this form. What is this? It's a fraction. A is the numerator value, B is the denominator value. If we can write any number in this form, we say those are rational numbers. So here B cannot be 0. Why B cannot be 0? When you divide any number by 0, you get math error. Math error means it goes to infinity. In other words, the value is not defined. So here, if you can write any number as a fraction, we call those are rational numbers. So what's the symbol we use for rational numbers? We use letter Q. Here, there's a line here. So here, first we'll take all types of numbers that we did and check whether these are rational numbers. For example, we'll take integers. We know integers are whole numbers. Can we write in this form? Okay, we'll take 7. 7 is a whole number. So we can write 7 over 1. So you can write as a fraction. What about 3? You can write as 3 over 1. What about 0? 0 divided by 1 is 0. Again, you can write any negative number. Negative 2 over 1. 23 over 1. So we see any integer we can write in this form as a fraction. So what can you say about integers? Integers are all rational numbers. So here we can write integers are rational. Now we'll take fractions. Okay, improper fractions, proper fractions. I'll write 2 over 3. So we can write in this form. 5 over 2. This is an improper fraction, but we can write as a fraction. What about negative? Negative half. That's also possible. It's a fraction. So we can take all fractions. Another one, 23 over 5. So we can see all fractions in this form. So fractions are rational or not? Fractions also rational. So fractions are rational. Now we'll look at decimals, terminating decimals. What are terminating decimals? So what are terminating decimal means? So the decimals ends. So here when you take 0.25, so there's an end to the digits. If you take 0.351, there's an end to that. So here we'll check whether terminating decimals are rational or not. So can we write this in fractions? 0.25, how can we write? we can write as a fraction 25 over 100. And then you can simplify and write. You can divide by 25. 25 times 1, 25 times 4. 1 over 4. So you can write this number, terminating decimal, as a fraction. What about this one? 0.351 you can write as 351 over 1000. So here that's also a fraction. So here any terminating decimal, 0.7, how can we write? We can write 7 over 10. This is the one decimal place number, so you can write 7 over 10. So here all these terminating decimals we can write in this form, A over B form. So what can we say about terminating decimals? Terminating decimals are also rational numbers. Now we'll take another type of decimals, recurring decimals. What are recurring? So recurring decimals means one digit or digits are repeating. So here we'll take 1/3, 1 over 3. So when you take 1 over 3, we know that 1 divided by 3, 3 times 0, 1 there for 10, 3 times 3, 9, again 10, 3 times 3, 9, again 10. So here can we see 3 is repeating again and again. So here 1/3 we can write 3, 3, 3. This is continuing. So we call these are recurring digits. So here one digit 3 is repeating. So when you take 0.333, 3 is repeating. So if we can write in another way that shows the concise value, we say that's the concise form. So here what we do, look at the repeating digit and we can write once only and then put a dot above the number. So we call this is the concise form. So we'll take another one. We'll take 2 over 3. Is it recurring? We'll see. 2 divided by 3. 0, 2 remaining for 20. How many 3s? 6. 18. Again another 20. 6. Another 18. So this one is 6 repeating. So what you say about this number? This is also a recurring decimal. How can we write this in concise form? We can write the repeating digit once and put a dot above the number. So this is the concise form. We'll take another example. So 3 over 11. Check whether this is a repeating decimal. So we'll take 3 divided by 11. So 11 times 0 for 30. 11 times 2, 22. So what's the next one? 30 minus 22 is 8. For 80, that's 7. 7 times 11 is 77. Another 3 remaining. For 30, 11 times 2. Again, 11 times 2 is 22. 30 minus 22, you get 8. Again, 80, this is 7. So what can you see now? Here, 2727 repeating. Here, 2 digits are repeating. So how can we write down this number in concise form? 2727. We see 2 and 7 both are repeating. So what we can do, we can write once and put dots above both these numbers. Now we'll take another one. 2 over 7. So is it repeating or recurring digit? So I'll use this side. We'll check that out. 2 over 7. So we'll divide 2 divided by 7. So what happens? Nothing there. 2 remaining. For 20, this is 2. 2 times 7, 14. 6 remaining. For 60, 7 times 8, 56. 4 remaining. For 40, 7 times 5, 35. 5 remaining. For 50, what's the number? 7 times 7, 49. Now 1 is there, 1 remainder, and when you take 10, that's 1. 7 times 1, 7. Now again 3. For 30, how many 7s? 7 times 4, 28. For 20, how many 7s? 7 times 2. 2 times 7, 14. 6 remaining. Now can you see again repeating from here? Again 7 times 8, 56. So here can you see this set of numbers are repeating in this case. So how can we write down this number in concise form? We can write as, so 2 over 7 is equal to 0.285714. That's the set of numbers repeating. So you write that once and then you can put a dot for the first one and the last number. No need to put dots for all numbers. So first and the last number we put dots. So that means the whole set is repeating. So now you know what are terminating decimals and what are recurring decimals. Now we'll look at how we can write down recurring decimals as fractions. So this is concise form. This means 3 is repeating. What about this one? 2 digits are repeating. 2, 7, 2, 7 like that. What about this one? 1 is not repeating but 3 is repeating. So here how can we write these numbers in fractions? So I'll teach you a method. So you need to follow the instructions. So we'll first see what's this number. This is only 3 is repeating. 3, 3, 3. So what about this one? 0.27, both dots are there. So that means 0.2727 like that. So what about this one? 0.1, only 3 repeating, not 1. Now we'll see how we can convert to fractions. So first we'll take this number as x. I can write just 3 numbers, but it's repeating. And then what we do, we multiply this by 10, 100 and 1000 like that to see, to get the same set of decimal digits. So we'll see first we can multiply by 10. So x multiplied by 10, you get 10x. So 0.333 multiplied by 10, you get 3.333 like that. Now what happens? Are we getting the same set of decimals here? Yes, after the decimal point, we see both these numbers 0.333 like that. So you have to stop the process till you get something like that. The decimals are the same. The set of decimals should be the same. Now, when we get the same set of decimals, what we do? We subtract the 2 equations. So here, what we can do, if this is 1 and this is 2, we can subtract 2 minus 1. That means bigger one minus the smaller one. So what happens to the left hand side? 10x minus 1x, you get 9x. Now when you are subtracting, what happens to the set of decimal numbers? The whole thing get cancelled out. So only you are getting the whole number. So that's the main idea when you want to convert recurring decimals to fractions. So here when you subtract, what happens? 3 minus 0, you get 3. So 9x is 3. So what is x? 3 divided by 9. You can simplify further. You can divide by 3 and write 1 over 3. So how can we write 0.3 recurring to fraction? So fraction is 1 over 3. Now we'll take this one. Now 2 digits are repeating. So how can we write down? Take that one as x. So I can write 0.2727. First step is to multiply by 10 and see. 10x, when you multiply by 10, one place moves to the right. So here you get 2.7272 like that. Now, are we getting the same set of decimals? No. So you need to do another step. So we can multiply by 10 again. That means 100. Multiply by 100, you get 100x is equal to, multiply by 100 means you shift 2 places to the right. So you get 27.2727. Now see, are we getting the same set of decimals? Here, look at first equation and this equation. You are getting the same set of decimal digits. So what we do, we take those two and subtract. Here I can subtract 2 minus 1, 100x minus 1x. So what is 100 minus 1? You get 99x is equal to, what happens here? The whole set get cancelled out. After decimal place, the whole set of decimal digits get cancelled out and you get 27 minus 0. So what is 27 minus 0? You get 27. 99x is 27. So what is x? X equals 27 over 99. Or you can simplify further, divide by 3 or divide by 9. 9 times 3, 9 times 11. So here we can write this recurring digit as 3 over 11. Now we'll take this one. Here one digit is repeating. So what's the first step? You take that one as x. Multiply by 10 and see. 10x equals, when you multiply by 10, you get 1.333 recurring. Are we getting the same set of decimal digits? No, not yet. So what's the next step? You need to multiply by 100. So 100x equals, what happens? You move 2 places now. 13.3333 like that. Now check carefully and see whether you are getting the same set of decimal places. Can you see? These two are the same set, 0.333. So we select those two now. You can label this one as 1 and this one as 2. So we can subtract these two. So 2 minus 1, what happens? 100 minus 10x now, 90x. So what happens here? 13 minus 1. So 13 minus 1 is 12. So what is x? X equals 12 over 90, or you can divide by 3, 4 over 30. Again you can divide by 2, 2 over 15. Now we'll see this number also we can convert to a fraction. So remember this method. Till you get the same set of decimal digits, you multiply by 10, 100, 1000, like that. Now we'll see a short method. Now we use the algebraic method to find out the fractions for recurring decimals. Now I'll teach you another method, a short method to convert recurring decimals to fractions. Why? Because fractions are rational numbers. So basically recurring decimals are also rational numbers. Now we'll take an example. We'll take 0.33. That means 0.3 dot. And we'll take the previous one as well. We took 0.27, 2 dots. And I can take any number, 1.2013 here. All 4 digits are repeating. And I can write 2.231 repeating. So here what we do, we need to see whether we can write down this in this form. So here I'll write down a minus b over 10 to the power x minus 10 to the power y form. What's a? A is the total number of digits. Without any decimals, we write the whole thing at once. So that's called A. So I can write all digits considered. B, I can write down digits up to the recurring decimal point. Digits up to the recurring decimal point. X is the total number of decimal places. And what is Y? Decimal places up to the recurring digit. We'll see how we can rewrite in this form. So what's the first step? We'll take this one. All digits considered. So without any decimals. So what's that? When you take all this one, you get 3. What about this one? Without taking any decimals, what's the number? 27. What about this one? Without taking any decimal, the number is 1000, 12,013. What about this one? You get without any decimals 223. Then we subtract digits up to the recurring decimal point. So up to the recurring point, we consider all the digits before that. So here this is the recurring digit. So what's the number before that? You get 0. What about this one? This is the first recurring digit. Before that, what you get? You get 0. What about this one? So all 4 repeatings, what's the recurring number? What's the number before the recurring digit? That's 1. What about this one? This is the recurring digit. What's the number before the recurring digit? 22. Now what you do? We divide this by 10 to the power, see total number of decimal places. So we see in this case how many decimal places are there? 1. So 10 to the power 1 minus 10 to the power. What's why? Decimal places up to recurring digit. So decimal place up to recurring digit, we don't have any decimal places. So here 10 to the power 0. So when you simplify, what you get here? 3 minus 0 is 3. 10 to the power 1 is 10. 10 minus 1. 10 to the power 0 means 1. So 10 minus 1, you get 9. When you simplify further, you get 1 over 3. Now look at this one, 0.27. Now, how many decimal places are there in total? 2 places. So 10 squared minus up to the first recurring digit, how many decimal places? We don't get anything. So here 10 to the power 0. So what's the answer? 27 over 10 squared is 100. 100 minus 1, you get 99. When you simplify further, divide by 9, 3 over 11. What about this one? What's the number? How many decimal places are there? 1, 2, 3, 4. So 10 to the power 4 minus how many decimal places up to the recurring digit? There's nothing. So 10 to the power 0. So what's the number? So when you subtract 1, you get 12,000. 12 over 10 to the power 4 means how many zeros? 1, 2, 3, 4. That means 10,000 minus 1. So what's the answer? You get 12012 divide by 10,000 minus 1. You get 9,999. And what about this one? How many decimal places in total? 10 squared. And up to the recurring place, how many decimal places? Now we have 1. 10 to the power 1. So when you simplify, what you get? 223 minus 22, you get 201. Divide by 10 squared is 100. 100 minus 10, you get 90. You can simplify this one. Divide by 3. 3 times 6, 18. For 21, 3 times 7. So you can divide 90 also by 3. You get 30. How can we write down this recurring digit as a fraction? This is 67 over 30. And what about this one? Here also, see whether you can simplify. This one you can divide by 3. So here 3 times 4, 3 times 4, 3 times 3, 3, 3, 3. So this is the fraction to this recurring digit. So this is the short method. If you can straight away, if you can remember this formula, apply and straight away you can convert any recurring decimal to a fraction. So fractions are rational numbers. So that's how you can show that recurring decimals are rational numbers. How can we identify whether the numbers are recurring decimals or terminating decimals? So here there's a small theory part. If we can write down in this form any decimal, if we can write in this form, here P is a constant, M, N also constants, and here I'll write P, M, N are constants, and you are not getting factors in the numerator and the denominator. No common factors. So if there are no common factors in the numerator and denominator, and if we can write any decimal number in this form, we can say it's a terminating decimal. If it's not written by this form, we call it, those are recurring decimals. Now we'll take some examples and we'll see how we can identify whether the number is recurring or terminating decimal. We'll take 7 over 20. So 7 over 20 we'll write in the other form. 7 you can write as 7. 20. How can we write 20? 20 we can write, first find prime factors, divide by 2, divide by 2 again, divide by 5. So how can we write down this number? 2 to the power 2 and 5 to the power 1. So we can write in that form, p over 2 to the power m into 5 to the power n. So if we can write in this form, so what we can say? This is a terminating decimal. So here this number is terminating decimal. Now we'll take this one. 6 over 100. First you can simplify. Divide by 2, you get 3 over 50. Now try 50 and see whether you can write in that form. Divide by 2, you get 25, 5, 5 and you get 1. So how can we write down? I can write 3 as it is, and this one I can write 2 to the power 1 and 5 to the power 2. So this is in that form. So what you can say, if you can write this form, that's a terminating decimal. Now we'll take this one, 3 over 125. How can we write 125? You can divide by 5. For 25, again you can divide by 5. So you can divide by 5 again. So how can we write down this? I can write 125 as 5 to the power 3. This is 1. How can I write 1 in terms of 2? I can write 2 to the power 0. 2 to the power 0 is 1. So here again, m and n can be any number, any constant. So 0 is also a constant. So here if I can write this form, this is a terminating decimal. We'll take this one, 11 over 16. So how can I write 16? 16 we know 2 to the power 4. So I can write 2 to the power 4. Instead of 5, I can write 5 to the power 0. This is also in that form. This is also terminating decimal. Now check 7 over 12. Can we write in this form? 12. How can we write 12? 12 divided by 2, you get 4, 6. Divide by 2, you get 3. Divide by 3, you get 1. So how can I write 12? I can write 2 to the power 2 and you get 1 3. Is that the form that we need? No, we need 5 to the power something. So now you get 3. That means this is not a terminating decimal. So what's that? This is a recurring decimal. Now we'll take 13 over 15. How can I write 15? I can divide by 3 and divide by 5. So I can write the denominator as 3 to the power 1 and 5 to the power 1. Here also you can't write 2 to the power m and 5 to the power n form. So that means this is also a recurring decimal. What about 17 over 200? So we'll try it out. 17 is there. 200, how can I write? 200 divide by 2, you get 100. Divide by 2, you get 50. Divide by 2 again, you get 25. So 25, 5 and 5. So can we write down in the other form? We can write 2 to the power 3 and 5 to the power 2. So here we can write this as 2 to the power m into 5 to the power n. So that means this is a terminating decimal. So now you know when you get any fraction how to identify whether it's terminating or recurring decimal. So what's the general form? P over 2 to the power m into 5 to the power n form. If you can write that in that form, we call those are terminating decimals. If you can't write in that form, we call those are recurring decimals. Now we'll look at the exercise 1.1 in your textbook. It says, for each of the following rational numbers, state whether it is a finite decimal or a recurring decimal. Express the fractions which are recurring decimals in decimal form and then write them in a concise form. So here it says finite decimal is same as terminating decimals. So here another name for terminating decimals, that's called finite decimals. Now we'll see whether we can write this number as a recurring form or terminating decimal form. Okay, we'll take 3 over 4. So what's the general form? If we can write down p over 2 to the power m into 5 to the power n form, those are terminating decimals or finite decimals. So we'll try to write down 4. We know 4 is 2 to the power 2. So 2 to the power 2 into we can write 5 to the power 0. So this is a terminating decimal. Or I'll write down here finite decimal. Now we'll take the next one, 5 over 5. We can write down, without simplifying, I can write down 5 over 5 to the power 1 and 2 to the power 0. So what you can say? This is also finite decimal. Next one, 3 over 7. Can we write in that form? 3 is there. 7, you can write 7 to the power 1 and you can write 2 to the power 0 or 2 to the power 5 to the power 0. But this is not in that form. So we can write this one is recurring decimal. What about this one? 5 over 9. Can we write down? 5, 9, we can write 3 squared. Here 3 is there. So here straight away we can say that's a recurring decimal. We'll take the next one. 5 over 21. Can we write? We know 21 is 3 times 7. Here you get 3 and 7. So that's not recurring. That's not terminating decimal. That's a recurring decimal. We'll take the last one. 7 over 32. How can we write down 32? 32 we know. Divide by 2, that's 16. Divide by 2, 8. Divide by 2, 4. Divide by 2 again, 2. Divide by 2, 1. How many 2's are there? 2 to the power 5. And we can write 1 as 5 to the power 0. Now we see you can write in that form. That means it's a terminating, or what's the other name for that? Finite decimal. Now they are asking, after we identify finite or recurring decimal, express the fractions which are recurring decimals in decimal form and then write them in concise form. So that means those who are recurring, we have to find out the decimal value. So we'll try to do this one. 3 over 7. How can we do 3 over 7? 3 divided by 7. 0 for 3. For 30, how many 7's? 4. That's 28. 20 is there. How many 7's for 20? You get 2. That's 14. Then 6 remaining. For 60, how many 7's? 8. 56. 4 remaining. For 40, how many 7's? 5. 7 times 5, 35. 5 remaining. Again, for 50, how many 7's? 7 times 7, 49. 1 remaining. For 10, 7 times 1, 7. 3 remaining. And for 30, 7 times 4. Now can you see? Again, now starting from that. So 7 times 4, 28. 2 remaining. For 20 again, 7 times 2. So here up to here to here, these digits are repeating. So how can we write down in concise form? We can write down this number 3 over 7 as, I can write 0.428571. Again 42857 repeating. So I can put 2 dots above first and the last digit. So this is the concise form of this recurring decimal. Now we'll take this one, 5 over 9. So we'll divide 5 over 9 and see. I'll erase this one and then I'll write down the next one. We need 5 over 9 as recurring decimal. So 5 divided by 9. For 5, there's no 9s. 5 remaining. For 50, how many 9s? 9 times 5, 45. Again, 5 remaining. For 50, how many 9s? 9 times 5, 45. So here, can you see 0.5 is repeating. 5 is repeating there. So how can we write down as concise form? 0.5, and then you can put 1 dot above 5. What about the next one? 5 over 21. So we'll see how we can find out the decimal value. We'll take 5 divided by 21. How many 21s for 5? Nothing. Then you get 50. So how many 21s for 50? 2. 2 times 21 is 42. Subtract, you get 8. For 80, how many 21s? You get 3. 3 times 1, 3. 3 times 2, 6. When you subtract, what you get? 17. For 170, how many 21s? If you take 6, 7, 8. 8 is also okay. 8 times 20, 9. You get 180 something. So here we'll take 8. 8 times 1, 8. 8 times 2, 16. So when you subtract, what you get? 20. For 20, are there any 21s? No, nothing. For 200, how many 21s are there? If you take 9, you get 9 times 1, 9. 9 times 2, 18. So here, what's the remaining part? You get 1 here, 1 here, 11. So 110, how many 21s are there? When you multiply by 7, you get 14. So 6, that's more than that. So it's 5. 5 times 1, 5. 5 times 2, 10. What's the remaining part now? 10 minus 5 is 5. Then 0. So 5 remaining. Again, can you see 50 there? It's repeating from here. So again, you are getting 2. So that means this number repeating from here to here. So how can we write as concise form? We can write 0.238095. We can put 2 dots above the first decimal place and the last decimal place. So that means the whole set is repeating. Now we'll take 19 over 33. And we'll see whether we can write as 2 to the power m into 5 to the power n in the denominator. So here 33 is 3 times 11. So it's a recurring decimal. Now we need to write down in the concise form. Now how can we write down in concise form? You have to do long division and see. 19 over 33. 0. And for 190, how many 33s are there? When you multiply by 6, you get more than 190. So this should be 5. 5 times 3, 15. 1 remaining. 5 times 3, 15 plus 1, 16. When you subtract, you get 25. Then for 250, how many 33s are there? Multiply by 7, you get less than 250. 7 times 3, 21. 2 remaining. 7 times 3, 21 plus 2, 23. Now subtract 19. Again, now see how many 33 is 490. When you multiply, you get 5. 5 times 3, 15. 1 remaining. 5 times 3, 15 plus 1, 16. When you subtract, you get 25. Now, can you see it's repeating again, 257. So 5757. How can we write in concise form? I can write this as 0.57. Both are repeating, so I need to put 2 dots above 5 and 7. Take the next one. 13 over 50. Can we write down the denominator in 2 to the power m and 5 to the power n? 50 is, when you take 50, you can divide by 2 for 25, 5 and 5. 5 squared. So here you can write 2 into 5 squared. 2 to the power 1 and 5 to the power 2. This is a finite decimal because you can write this as 2 to the power m and 5 to the power n. Third one, 7 over 64. 64, how can we write down? 2 to the power, we know 2 to the power 6 is 30. 2 to the power 6 is 64. We'll just divide and see. How many 2's? 2 to the power 6. I can write 64 as 2 to the power 6. Instead of this one, I can write 5 to the power 0 because 1 is 5 to the power 0. You can write in this form. That's a finite decimal. Now look at the next one. 5 over 18. 18 is 2 times 9, 3 times 3, 3 times 1. 2 and 3 squared. It's not in this form. It's a recurring decimal. Now we need to find out what's the concise form. 5 divided by 18. I'll erase this one and get space here. 5 divided by 18. For 50, how many 18s? When you multiply by 2, you get 2 times 8. 16, 1, 2 times 1, 2 plus 1, 3. When you subtract, you get 14. For 140, how many 18s are there? Multiplied by 7. 7 times 8, 56. 5 remaining. 7 times 1, 7. 7 plus 5, 12. You get 14. Can you see? Again and again you are getting 7, 7 like that. What's the concise form? I can write this one as 0.27. Only 7 is repeating. Take the next one. 15 over 128. 128 can we write as 2's and 5's. When you divide by 2, you get 64. Divide by 2, you get 32. You can. This is repeating all 2's. What's the power? I can write 128 as 2 to the power 7. And instead of this, I can just write 5 to the power 0 because 5 to the power 0 is 1. You can write in this form. This is a finite decimal. 41 over 360. 360, when you divide, what you get? 3 times 1, 120, 3 times 4, again 2 times 20, 2 times 10, 2 times 5. How many 2's? 1, 2, 3. You get 2 to the power 3. How many 3's? 2 3's and 1 5. The denominator is not in this form, so this is a recurring decimal. Now we'll need to find out the concise form. We'll take long division. I'll take space here. (41) over 360. This is nothing. For 410, it's 1. When you subtract, you get 50. For 500 again, you are not getting double, so this is 1. 360. Subtract 140. For 1400, how many 360's are there? When you multiply by 4, it's more than 1400. So it's 3. 3 times 0 is 0. 3 times 6, 18. 1 remaining. 3 times 3, 9 plus 1, 10. Subtract. You get 320. Again, we'll divide. How many 360 is for 3200? Multiplied by 8. Multiply by 8. 8 times 0, 0. 8 times 6, 48. 4 remaining. 8 times 3, 24 plus 4, 28. You subtract, you get 320 again. Now can you see? Again 3200. Now it's repeating again. What's the concise form? 8 is only repeating. I can write this as 0.113. Only 8 is recurring. So I can put a dot above 8. Now we'll see how we can identify a fraction is terminating or a recurring decimal at once. Without doing long division, how can we identify at once? So here we know that if you can write down the fraction as p over 2 to the power m into 5 to the power n, we know those are terminating decimals or finite decimal. So here terminating, or we can write down finite decimals, and we can write what are recurring decimals at once by looking at the denominator. Okay, so here if you can write any number over 2 to the power m and 5 to the power n, we know that those are finite decimals. So we'll see only the denominators, and if you can write down that number as a multiple of 2 and 5, that means it's a finite decimal. If you can't write in that form, that's a recurring decimal. So 50, how can you write? 50 is 2 times, when you divide by 2, you get 25, and 5 times 5, 2 and 5 only. So that means 13 over 50 is a finite decimal or terminating decimal. What about 16? We know 16 is 2 to the power 4. So if you can write as a multiple of 2 or 5, that's a terminating decimal or finite. So 9 over 16 also a finite decimal. What about 24? 24 you can divide by 3. 3 is a factor. When you get 3, we know that's a recurring decimal. So 5 over 24 is a recurring decimal. What about 12? 12 is also 3 times 2 times 2. That's also a recurring decimal. What about 8? 8 is 2 to the power 3. So that means a multiple of 2, that's a terminating decimal. 18, 2 times, 3 times, again 3. So that you get 3 as a multiple. So 13 over 18 is a recurring decimal. What about 100? 100 is 2 to the power 2, 5 to the power 2. So 100 you can do, divide by 2, you get 50, divide by 2, you get 25, and 5 and 5. So 2s and 5s are multiples. So you can say that's a terminating decimal or finite decimal. What about 40? 40 you can write, divide by 2, divide by 2 again, divide by 2, and you get 5. 2s and 5s only. So that means that's also a terminating decimal or finite decimal. What about 21? 3 times 7. So that's a recurring decimal. What about 9? 9 is 3 times 3. So that's a recurring decimal. 200. So 200 is 100 times 2. We know that when you take 100, that's 2s and 5s. So again you are multiplying by 2. So that means that's also terminating decimal or finite decimal. What about the other one? 20. How can I write 20? 2 to the power 2 into 5. So that's a terminating decimal. So here when you look at the denominator, you can easily identify whether it's a terminating decimal, finite decimal, or recurring decimal. Now we'll look at what are irrational numbers. So we know what are rational numbers. If you can write any number as a fraction, we call those are rational numbers. So irrational means opposite thing. If you can't write in a fraction form, we call those are irrational numbers. So what's the symbol we can use? We can use Q dash for irrational numbers, not a rational number. So this is a set notation. Dash means outside Q. That means not a rational number. So here when you see Q dash, that means irrational number. So what are irrational numbers? So in grade 10 you have done square roots. We'll take square root 2. Can you remember the value? Square root 2. We can find out approximate values. So what's the square root 2? You get 1.414. It's not ending. When you take root 3, what's the value we got? 1.732. That's also not ending. It's repeating, but not the same number repeating like recurring decimal. What about root 5? What's the root 5 value? 2.236 roughly. What about root 17? What's the value for root 17? 4.123. And also it's not ending. So here we call these numbers are irrational numbers because we can't write down the numbers in this form, cannot be written as A over B form, and B cannot be 0. If you can't write the number as a fraction, we call those are irrational numbers. Now we'll see how we can represent a line of length equal to irrational number. So we found out square root of 2, square root of 3. What about square root of 4? Square root of 4 is 2. That's not an irrational number. That's a whole number. So that's a rational number. Square root of 5, square root of 7. Those are irrational numbers. How can we represent that value using a line? So here, if we take, if you take length 1 and length 1 as the sides of a right angle triangle, if it's a right angle triangle, what you get here? According to Pythagoras theorem, this is hypotenuse squared is square of sum of squares of the other two sides. 1 squared plus 1 squared and take the square root. So what you get? 1 squared is 1, 1 plus 1, 2. You get square root 2. So that means when you consider this length, represent root 2 value. Now I want to extend this. Again, I want to draw a perpendicular line to this end with one length. So what happens now? When you draw that, you can again connect these 2 points. Now again you can use Pythagoras theorem. So root 2 squared plus 1 squared. What you get? Root 2 times root 2, you get 2 because square term and square root get cancelled out. So 2 plus 1, you get 3. So you get root 3 for this length. What about again if I draw a perpendicular line to this with one length? What I'm getting? Again Pythagoras theorem. Root 3 squared plus 1 squared and take the square root. Root 3 times root 3, 3. 3 plus 1, 4. Square root of 4 represent using this length. Again I can repeat the same thing. If I draw a perpendicular line with one length to this end and connect this length, what am I getting? Root 4 squared plus 1 squared and take the square root. So what you get? You get 4 plus 1, 5, root 5. So here you can find out the line with all these irrational numbers. So here we can find any irrational number using this method. So who found out this method? So a mathematician called Theodorus. So here Theodorus. So here the mathematician called Theodorus. So we call this is as root spiral of Theodorus. So here using this method we can easily draw any irrational number. Now we'll look at how we can represent irrational numbers on a number line. So here I want to draw on a number line. Now we'll see. We know number line. We can draw 0, 1, 2, 3 with equal distance. And here we want now root 2 value. So we know according to root spiral of Theodorus, we know when you take a right angle triangle with one length, you get root 2. So we use that method. So I am now constructing a right angle triangle with one length here, one length there. So what I get? I get a triangle with this length equal to root 2. So what I can do, I take the compass, take this distance, that's root 2, and draw an arc. So when you draw an arc, what happens? This distance also the same size. You get root 2. So this point is root 2 value. So root 2 is 1.414 roughly. So this value you get root 2. How can I get root 3? Now we know according to root spiral of Theodorus, when you draw one length to root 2 value, you get root 3 value. So we'll use that method. Now we know this length is root 2. Now I am drawing a perpendicular line to that with one length. So here same height. I can take the same height. So here something like this. So this is one distance. Now I am drawing this line. Connect this point with this one. Now root 2 squared and 1 square we know according to Theodorus, that's root 3. So again what I can do, I can take the compass, keep this length and draw an arc. When I draw this arc, we know this length represent root 3 value. So you can repeat the same thing again and again to get the root values of any irrational number. Here we can find out square root of any whole number. So here when you draw the arc, this should pass through 2 because root 4 is equal to 2. So using this method, you can find out any value on the number line, whether it's rational or irrational, any number you can draw on this number line. So here, what are then rational numbers? If we can draw on a number line, we call those are rational numbers. So now we saw we can represent, if this is a number line, we can represent irrational numbers. We can represent integers or natural numbers, counting numbers. Fractions, yes, we can represent fractions, 0.5, 0.75. And terminating decimal or finite decimals, yes, 0.5, 0.51. We can show on a number line. What about irrational numbers? Yes. So when you take a number line, you can show any number on that. So we call this line as real line. So real line means we can show any real number on the number line. Fractions, decimals, whole numbers, integers, and also irrational numbers. So if you take any Cartesian plane, x and y plane, we call Cartesian plane. Here this is also like number line. So here we call this is the real plane because we can show any number on that plane. So here if it's a Cartesian plane, we call that's a real plane. If it's a number line, it's a real line because we can show all these numbers on a number line as well as Cartesian plane. Now we learn several types of numbers. Real numbers, irrational, rational, integers, natural numbers, everything. Now we'll try to use a Venn diagram to show all these numbers. You know Venn diagrams? We can take the whole set of numbers as a rectangle. So we know all real numbers. So here we can take this rectangle as real. That's real numbers. And we know when you take real numbers, we can find out what are rational numbers. So rational we denote it by Q. Now what are the numbers outside rational and inside real? We know outside rational means irrational numbers. So what are irrational numbers? Root 2, root 5, root 6. Those are irrational numbers. And also there's another special number we used before. Pi value. We know pi value is 3.14, like it's not ending. So you can't, even though we write 22/7, that's an approximate value, not exactly 22/7. So because of that, we can take this pi value also as an irrational number. So we can write down outside. Now we know inside numbers are rational. Any fractions, decimals. Then we can again think about another set called integers. So Z letter represent integers. So what are integers? Integers are whole numbers. It can be negative or positive. So here if you take outside integers and inside rationals, we can write any fraction value, any decimal value, or any recurring decimal, because recurring decimal is also rational. And terminating decimal, finite decimals, fractions, anything outside integers, because integers are whole numbers. Now inside whole numbers, there's another set we learnt. Those are called natural numbers. So natural numbers means n. Counting numbers. So here inside natural I can put 1, 2, 3, any integer, positive integer. Or I can write instead of n, this is z plus. because z plus means positive integers are same as natural numbers. And what are the numbers outside natural and inside integers? Any negative whole number, -3, -1. And also I can write 0. 0 is also an integer but not a natural number. So here this is the whole set of real numbers. So here in A-level class you will learn another set outside the real, that's called complex numbers. Now we'll look at exercise 1.2 in your textbook. It says state whether the following real numbers as rational numbers or irrational. So how we identify rational? If you can write as a fraction, it's rational. If it's repeating or never ends, it's an irrational number. So root 2, we found that it's irrational. What about root 25? Square root of 25, we know that's 5. So, is it rational or irrational? 5 is a whole number, that's an integer. Integers are rational. What about root 6? It's not a whole number, so that's irrational. What about root 11? That's also never ends. So here that's an irrational number. What about 6.52? That's a finite decimal. Finite decimals you can convert to fractions. So those are rational numbers. Now we'll look at question number 2. It says determine whether each of the following statement is true or false. First one, it says any real number is a finite decimal or an infinite decimal. So what is infinite decimal means? Irrational. There's no end to that. Finite means terminating decimal. So here any real number is finite or infinite. Can we say it's correct? Finite means terminating decimal. Infinite means either it can be recurring decimal or irrational number. So here both rational and irrational numbers are real numbers. So this statement is true. What about this one? There can be rational numbers with infinite decimals representations. So infinite decimals means irrational numbers. So here rational numbers with infinite decimal, recurring decimals. So here they are talking about recurring decimals. So those are recurring decimals are rational. So it's true. Any real number is a recurring decimal or an infinite decimal. What about definite decimals? They are not talking about definite decimals. So because of that, this statement is false, because not talking about definite decimals. What about this one? Is it a recurring number? Here 0, 1, but the next time 0, 1, 1, 0, 1, 1, 1. This is not a recurring decimal. So recurring decimals are rational. So this is an irrational number. So it's not rational. So the statement is false. Now we'll look at what are surds. So here in grade 10, you know about this symbol. What's that? Square root symbol. So if we can write any numerical value in this form, We call these are surds. Now here we call, if you get this symbol, that's called radical form. So here you can get whole numbers, you can get decimals, you can get any number. We'll say 231, any whole number, or you can get radicals like this here, 3 outside, and you get any number here. So here there are several forms of surds. So you can get something like this, something like another number here. So what are those? Here we say this is square root. But when you get number 3 outside, we say cube root. Cube root of 5, fourth root of 6. And also you can get something like this. Radical form with any big number, 200. And also you get a whole number and a radical value like this. It can be negative. So here, if we can write down any numerical value, it can be decimal or whole number inside the radical form, we call those are surds. So all these type of numbers are surds. So here, if we can write like this, we call that's a normal surd. But if we can write the whole number inside, we call these are entire surd. So you need to remember the words. If there's a number only inside the radical form, we call entire surd. So in your syllabus, we need to only think about radicals with whole numbers inside. Now we'll see how we can simplify entire surds. What are entire surds? Any whole number in the radical form. So this is a entire surd. How can we simplify and write down as a surd value? So here what we need to think about, how can we write down 12 in terms of a square number and another number? Then we can simplify further. If you can write down 12 in terms of a square number, we can simplify. Now we'll see 12, you can divide by 2, you get 6, divide by 2, you get 3. Now I can see one pair is there. That means 2 to the power 2. 2 squared is 4. 4 is a square number. So I can write 12 in terms of 4 and 3. If I can write like that, you can easily simplify. Now square root of 4, I can write separately and multiplied by square root of 3. So what is square root of 4? We know square root of 4 is 2. So I can further simplify. Instead of square root 4, I can write 2 and you get root 3. So now see, root 12 is equal to 2 root 3. So we can simplify an entire surd to a surd value. Now we'll take 20. What's the maximum square number we can get for 20? So we'll take 20 and see. 20 you can divide by 2. Again 2. You get 5. Can you see? This is a square number. One pair is there. 4 times 5. So I can write 20 as 4 times 5. Then I can write separately square root of 5 and square root of 4. So what's that? Square root of 4 is 2. You get 2 root 5. What about 8? What's the square number for 8? When you divide by 2, you get here one pair of 2. So here 4 times 2. So square root of 4, square root of 2. Square root of 4 is 2. You get 2 root 2. What about 200? You can divide by 2, divide by 2. You can divide by 2 again, and 5 and 5. Now we get 2 pairs, 2 and 5. So here what's the square number here? This is 25, this is 4. 25 times 4 is 100. 100 is a square number. So I can write 200 as 100 times 2. Then we can write down separately square root of 100 into square root of 2. Square root of 100 is 10. You get 10 root 2. What about 98? What's the square number you can get for 98? When you divide by 2, you get 49. Then you can divide by 7 and write 7 times 7. So what's the square number here? 7 times 7, that's 49. So I can write instead of 98, 49 times 2. And then square root of 49 separately and square root of 2. Square root of 49 is 7. So 7 root 2. What about 72? 72 I can divide by 2. You get 36. Divide by 2. You get 18. Again divide by 2. 9. Again by 3. You get 1. So what's the square number? See how many pairs are there? I see 2 pairs. 3 into 3 is 9. 2 into 2 is 4. 9 times 4, 36. So instead of 72, I can write 36 times 2. Square root of 36 is 6. Square root of 2 you get here. So what's the answer? 6 root 2. So when you can find out any number with a square term, you can simplify further. Now we'll take algebraic expressions like this. So again 27 you have to write as a square term. So what is 27? You can divide by 3, divide by 3, divide by 3. So here you get one pair. 3 times 3, 9. 9 times 3. And a squared is there. A also here I can write multiplied by a squared. Now I can take separately square root of 9, square root of 3 and square root of a squared. What am I getting? Square root of 9 is 3. What's the square root of a squared? You get a. What's the square root of 3? Square root of 3 remaining. So 3a root 3. What about 75? How can I write 75? Divide by 5. You get 15. Divide by 5 again. You get 3. So you get 25 times 3. So I can write this one as 25 times 3 times y squared. Take it separately. Square root of 25, square root of 3 and square root of y squared. So what is square root of 25? You get 5. Square root of y squared, you get y and root 3 remaining. What about 32? You can divide by 2, divide by 2 again, divide by 2, 2 and another 2. So how many pairs are there? 1, 2. So what's the square number? 2 times 2, 4. 4 times 4, 16. So 16 times 2. Then take square root separately. I can write square root of 16 as 4. Square root of m squared is m. And then square root of 2. What about 500? How can I write 500? We know 500 is 100 times 5. 100 is a square number. I'll straight away write down 100 times 5. Then I can write square root of 100 and square root of 5. What is square root of 100? You get 10 root 5. What about 300? Similarly, I can write 100 times 3. When you take separately, you get square root of 100 into square root of 3. Square root of 100 is 10 and you get square root of 3. What about 147? We'll divide and see. Divide by 7, you get 21. Divide by 7 again, you get 3. So what's the square number you get? 7 times 7, 49. So you can write this one as 49 times 3. And then when you take the square root, we get 49 square root and 3 square root. And what's square root of 49? You get 7 root 3. Now we'll see when you get a surd value, how you convert this to an entire surd. So here, reverse process of the earlier one. So here earlier we did surd, entire surd to a surd value. Now surd value is given, you are asked to write as an entire surd. So how can we do that? So reverse process. Without taking outside, we are putting the number inside the radical form. So what we can do, we'll write 2 as it is, and here 2 we need to take inside. So when you are taking inside, you get square term because 2 squared is 4. Square root of 4 is 2. So here when you are taking 2 inside, it becomes the square term. So what is 2 squared? You get 4. Then you just multiply the inside numbers. 2 times 4, you get 8. So the entire surd is root 8. Here, what's the number outside? We need to put this inside. So you take 5 squared. So what is 5 squared? 5 squared is 25 times 3. So what is 25 times 3? You get root 75. So when you put 7 inside, what you get? 7 squared. 7 squared is 49. So 49 times 2. So what is 49 times 2? You get 98 square root. What about this one? When you take 11 inside, it becomes 11 squared. So what is 11 squared? 121 times 2. What's the answer? You get 242 square root. Here 2 inside, you need to take that one inside. 2 squared is 4. 4 times 11, you get root 44. What about this one? You are taking 4 squared inside. What is 4 squared? 16 times 2. When you take square root, 2 times 16 is 32. So this is square root of 32. Now we'll take algebraic expressions. So you have to take this whole thing inside. So how can I write? 3a times 3a. 3a squared is 9a squared. So I can write inside 9a squared into 3. So 9 times 3, 27, a squared and this is square root value. What about this one? 2b root 11. I can take 2b square term inside. 2b times 2b, 4b squared. So I can write 4b squared into 11. So what's the answer? 44b squared square root. What about this one? 4m. When you square it, 4m times 4m. 16m squared into 2. 16 times 2, you get 32m squared. This one, you have to take 8 squared inside. 8 into 8, 64. 64 times 3a. What's 64 times 3? 3 times 4, 12. 1 remaining. 3 times 6, 18. Plus 1, 19. A. This one, whole 3x squared. 3x into 3x, 9x squared. So 9x squared into 2y inside. When you multiply 9 times 2, 18, x squared y. This one, 5p, you have to take the square term inside. 5p times 5p, you get 25p squared into 2q. You get 25 times 2, you get 50 p squared q square root. Now we'll see how we can add or subtract surds. Now look at this expression. This is a surd value, another surd value. So here I'll show you this with two methods. So first thing I can do, I can check the common term. I see root 2 is common to both expressions, so I can take it out. When I take root 2 out, what's remaining? 3 plus 4. We know 3 plus 4 is 7. So 7 root 2 you are getting as the answer. But without taking the factors out, I can take algebraic method. So if I take the surd value as x, this root 2, same surd value you are getting. So I can write x as root 2. So what is this one? 3x. What about this one? 4x. What is 3x and 4x? I can write 7x. After you find out the addition, I can plug root 2 instead of x. So what's the answer? 7 root 2. So here this method is easier than this. So when you get the same surd form, you can add the integers in front of those surds. Now look at this expression. Look at carefully what are the like terms where you get same surd values. This one and this one, same surd form. So you can add it together. 5 plus 3, you get 8 root 3. When you take this one and this one, you can add separately. So what's the answer? Root 2 is the surd value. 2 plus 5 becomes 7. So when you want to add surd values, you can add same surd values and simplify. Now we'll take subtraction. So here I can see root 5 is common. I can take it out. What's remaining? 7 is there, minus 3. We know that 7 minus 3 is 4. So I can write this one as 4 root 5. What's the shortest method? You can write the surd value as x and c. So I can write 7x instead of 7 root 5. I can write 3x instead of 3 root 5. So what is 7x minus 3x? You get 4x. Now I can plug x as root 5. So you are getting the same answer. So when you get same surd value subtraction, you can just subtract the integers in front. Now we'll use that method. Now we have combination of pluses and minus. So what we can do? So first check the same surd value. So here this and this. So you get minus. What you do? 11 minus 2, you get 9. And then you get the same value of surd. Then you can simplify these two because surd value is 2. 7 minus 5, you get plus 2. So you can write 2 root 2. What about this one? Only same surd values you can add or subtract. Here root 5 here. Root 3 here. But root 2 you can't simplify. So 11 minus 7, you get 4. 4 root 5. What about this one? 4 minus 2, you get 2 root 3. 4 minus 2 is 2. Then you can write down 5 root 2 as it is. You can't add these three because different surd values. What about this one? Identify like terms. Same surd values you can add or subtract. Root 5, you are not getting any term. So, but root 3, this and this. And root 2, this and this. So, you can simplify only those two. So, 6 root 5 you have to write as it is. Then what about root 3? 11 minus 2. What is 11 minus 2? You get plus 9 root 3. What about minus 2 plus 7? So, minus 2 plus 7 becomes 5. So, you get 5 root 2. But after that you can't simplify because the root values are different. Different surds you can't add or subtract. What about the other one? Next one. What are the like terms? 6 root 5, 7 root 5, 10 root 5. The other one we can simplify these two. 4 root 3 and 2 root 3. So here what we can do, root 5 values, 6 plus 7, you get 13. 13 minus 10, you get 3. So you get 3 root 5. What about these two? 4 minus 2. So 4 minus 2 becomes 2 root 3. So that's how you add or subtract surd values. Now we'll see you need to add or subtract after simplifying these surds. Otherwise you can't add or subtract. Can you see different surd values there? If you can simplify and write as the other forms, maybe you can simplify further. We'll look at the first question. 2 root 8. Can we write root 8 in surd form? That's an entire surd. Try to simplify root 8. I can write root 8 as 4 times 2. Try to find out whether there's a square number. So 8 I can write 4 times 2. What about this one? 12. Can I simplify further? 12 I can write 4 times 3. This one I can't simplify further. This one I can't, so I can write as it is. Now we'll simplify this one. So when you are simplifying, I told you you can take separately. So root 4 and root 2. So here 2, root 4, root 2. What about this one? You get root 4, root 3. This one you write as it is. Now, we know root 4 is 2. 2 times 2, 4. So, I can write 4 root 2. Root 4 is 2. 2 times 3, 6 root 3 minus 2 root 2 and 2 root 3. Now, you can add or subtract. What are the like terms? This and this with this. 4 minus 2, you get 2. What about this? This one. 6 minus 2, you get 4 root 3. Now we'll look at this question. Root 18. Can we write down 18 as a square number? Yes, we can. We can write, that's 9 times 2. Can we write 20 as a square number? What's a square number? 4. 4 times 5. And this one you can't simplify. This one you can't simplify further. Now these two you can simplify. Again write as root 9 and root 2 here. This one root 5 and root 4. This one as it is. Now simplify. What is root 9? Root 9 is 3. 3 times 5, 15. Root 4 is 2. 2 times 2, 4. Now you can simplify same surd value. So these two together, these two together. So what is 15 minus 10? You get 5. What is 4 minus 3? You get 1. So 1 root 5 you can, without writing 1, you can write root 5. We'll take some more examples. 50. Can we simplify 50? How can we write down as a square number? I can write 25 times 2. What is 75? I can write as 25 times 3. This one I can't simplify. This one I can't simplify further. Now write separately. I can write root 25, root 2 here, root 25 and root 3. This one you have to write as it is. Now try to simplify. Root 25 is 5. 11 times 5, 55. What about this one? Root 25 is 5. 5 times 4, 20. This one you can write as it is. Now try to simplify. This and this, this and this. So what is 55 minus 18? You get, what's 15 minus 55 minus 18? You get 37. So 37 root 2. And what is 20 minus 5? You get 15 root 3. Now we'll look at this question. Root 80. How can I write root 80? What's the square number? We'll find out what's the square number. When you divide by prime numbers, you can identify what's the square number. One pair, another pair. So 4 times 4, 16. So 16 times 5 is 80. So you can write 16 times 5. 20, how can I write? As a square number, 4 times 5. 45, what's the square number? 9 times 5. What about this? You can't simplify this one. 50 again. 50 you can write as 25 times 2. Now try to simplify. Root 16 into root 5. This one, root 4 and root 5. This one I can write root 9 and root 5. This one you can't do anything, just write as it is. This one root 25 and root 2. Now what's square root of 16? 4. I can write this one as 4 root 5. What about this one? Square root of 4 is 2. 2 times 3 is 6. I can write 6 root 5. What about this one? Root 9 is 3. 3 times 2, 6. I can write 6 root 5. This one I have to write as it is. What about the last one? 25 square root is 5. 5 times 2, 10. Now we'll see how we can simplify. These three terms I can simplify further with these two separately. So here 4 plus 6, 10, 10 minus 6, you get 4. So this is 4 root 5. 17 minus 10, you get plus 7 root 2. So that's how we can simplify. Now we'll look at multiplication and division of surds. Earlier we discussed addition and subtraction. So now we'll see when you get a multiplication sign, how we simplify these surds. Now what we do, we can multiply the numbers in front separately and the surd values separately. So I can write this one as 2 times 3, 6, and then inside I can multiply these two. 3 times 6, 18. Then what we do, we can simplify this number inside the radical form if we can convert to a square number. So 18, how can I write as a square number? 9 times 2. So I can write 6 and then instead of 18, 9 times 2. Then what I can do? I can write separately. You get square root of 9 and square root of 2. But we know square root of 9 is 3. So 3 times 6, you can multiply and write 18 and square root 2. Again, this one, you multiply the numbers separately. 3 times 2, you get 6. What's inside? You get 12 times 6 inside. So 6 times 2, 12, 1 remaining. 6 times 1, 6 plus 1, 72. Now we need to find out what's the square number of 72. What's the number? 36. So you can write 72 as 36 times 2. So again we can write separately square root of 36, square root of 2. What is square root of 36? That's 6. 6 times 6, 36. So you get 36 root 2. Now look at this one. There's nothing means just 1. So 3 times 1, you get 3. When you multiply the surd values separately, 7 times 8, 56, 5 remaining. 7 times 2, 14. 14 plus 5, you get 19. So 196. So what's the square number of 196? We'll divide and see. 2 times 9, 18. 8, 2 times 4, 9, and I can see 7 and 7. Here, what's the square number? This is a perfect square. So what's the perfect square? 7 squared and 2 squared. So how can I write this one? So what's the square root of 196? I can write 3, 7 squared and 2 square. So in grade 10, you learned how to find out the square roots. So here square root and square term get cancelled out. What you get? 3, 7 and 2. So what's the answer? 7 times 3, 21. 21 times 2, 42. This one, you can multiply separately the whole numbers. 3 times 2, 6. Then you get inside 63 and 28. Here without multiplying, we'll try to find out the prime factors. 63, what are the prime factors? You get 3 squared and 7. 28, when you divide, you get 2 squared and 1 7. Now can we see? We can rewrite this as 6 square of 3 square of 7 again, square of 7 and square of 2. So we know when you take square root and square term get cancelled out, and finally we get 6 times 3 times 7 times 2. So what's the answer? 3 times 2, 6. 6 times 6, 36. So what is 36 times 7? 7 times 6, 42. 4 remaining. 7 times 3, 21 plus 4, 25. So 252. Now we'll look at how we divide surd values. So here what we can do, we can rewrite the division form to a fraction. So I can rewrite this as 6 root 56 divided by 3 root 2. Then what I can write? I can just simplify the whole number separately and the surd number separately. So I can rewrite 6 divided by 3, you get 2. This one I can write as one single radical form and write down 56 over 2. What is 56 over 2? You get square root of 2 times 2, 4, 2 times 8, square root of 28. Then try to write down this number as a square number. 28, what's the square number? 4 times 7. So I can write 4 times 7 and simplify further as square root of 4, square root of 7, and I can write square root of 4 is 2, 2 times 2, 4, 4 root 7. Now we'll look at this one. Use the same procedure. You can rewrite this as division value as a fraction. Then simplify the whole number separately. 30 divided by 6 is 5. Then do this one separately. So I get 5 square root of 225 over 3. So what is 225 over 3? I get square root of 3 times 7, 21 for 15. That's 5. So 75. So what is 75 as a square number? I can write this as 25 times 3. Then write it separately and simplify. Square root of 25 is 5. 5 times 5, 25. So you get 25 root 3. Now we'll do this one. Write separately. Now here 1 over 2. Now you can write as a single fraction. So I can write 48 divided by 3 and 2 in the denominator. So what is 48 divided by 3? I get 3 times 1, 3, 3 times 6. Square root of 16. So what is square root of 16? Square root of 16 is 4. 4 divided by 2, I get 2. What about this one? I can write as 24 root 35 over 8 root 7 and 8 times 3 I can simplify and then write as a single radical form 35 over 7. So we know 7 times 5 is 35. So what's the answer? You get 3 root 5. This one, try now. Again write the number in this form and then simplify the whole number. This part you can write as a single radical form 126 over 2. So simplify that. You get 2 times 6, 2 times 3. 63. How can I write as a square number? Divide by 3, you get 21. Divide by 3, you get 7. So here square number is 9 times 7. So I can write this one as 9 times 7. What's the square root of 9? That's 3. So you get 3 times 3, 9. The answer is 9 root 7. Now we'll look at when you square Surds value, what will happen. Now we'll take root 2 and I want to square it. What is root 2 times root 2? So here I can write as one single radical form 2 times 2. You get square root of 4. Finally, you get square root of 4 is 2. Now take root 3. Root 3 times root 3. When you write as a single one, you get 3 squared. 3 times 3, 3 squared. And when you simplify, you get 3. When you take x, what happens? Root x times root x. Again, you can take it at once, x into x square, and root value. When you take square and square root, it get cancelled out and you get x. So what's the pattern you see? When you square any surd value, the surd form get cancelled out and you get only the number inside. Here also you get 3. Here you get x. So remember this, when you get any number a and take square root, and if you want to square it again, you get the same value as the inside number. So when you know this pattern, you can easily substitute and get the answer. Now we'll look at rationalize the denominator. What it means? Rational number in the denominator. Now we'll take something like this. 1 over root 2. Can we find out that value? We know root 2 value is 1 over 1.414. Then if I ask to find out this value, what you do? You have to convert this to a whole number and do long division. So it takes time. We'll see if we want this one to find out, we have to use long division. But now here, can you see this is the numerator and this is the denominator. What's in the denominator? It's an irrational number. rationalize the denominator means we are trying to get rid of this irrational number to a rational number. But why we are doing that, we'll see. When you want to find out this answer, you have to do the long division. So we'll see. I can multiply this by 1000 and write 1000 divided by 1414. What's the answer? I can write 1000 divided by 1414. Nothing for 1000. So you get how many 1414 for 10,000? If I put 9, that's more than. If I put 8, what's the answer? It's less than 10,000. So I'll put 8. It's more than that. So I'll put 7. 7 times 4, 28. 2 remaining. 7 times 1, 7. 7 plus 2, 9. 7 times 4, 28. 2 remaining. 7 times 1, 7. 7 plus 2, 9. When you subtract, what you get? 10 minus 8 is 2. 9 minus 0. 9 minus 8, 1. So 102. So then divide it again. 1020. So you don't get 1414. So here we put 0. Then you have to look at for 10,200. So 10,200 again, you get 7. 7 times 4, 28. 2 remaining. 7 times 1, 7 plus 2, 9. Here we did the multiplication. And when we subtract, what you get? 10 minus 8 is 2. 9 minus 9, 0. 11 minus 8 is 3. So 302. And again, if you want this number, you are doing this again and again. So roughly 0.707. So I can write this answer as 0.707. Now will you use another method and see whether we can find the answer easily. I am now getting rid of this surd value in the denominator. So that's called rationalize the denominator. How can I get rid of this root 2? So what I can do, I can multiply both the numerator and the denominator by the same surd value. So what happens when you do that? 1 times root 2, you get root 2. Root 2 times root 2. We did squaring root values, surd values. You get the same surd. Now, what can we see? This surd value now becomes a whole number. So that's called irrational number, we rationalized. So rationalize the denominator. Now, how can we find out this answer? We know root 2 is 1.414. Divide by 2. So what's the answer? This is roughly. So divide by 2, you get 0.707. Can you see? Without doing long division, we can easily find out the answer when you rationalize the denominator. So remember that when you get something, a surd value in the denominator, first you rationalize it and then you can find out the answer. Now we'll take another example. We'll see if root 3 is, we know, 1.732. How to find out the answer for 1 over root 3. So here in this one you get a surd value in the denominator. So what's the easiest way to do? You rationalize the denominator and then substitute the value. So here, take the surd value, rationalize it. So when you rationalize, you multiply with the same surd value. So what happens here? 1 times root 3 is root 3. Root 3 times root 3 becomes 3. Now you can plug the value. So what is root 3? 1.732. Here you have to write down the approximation sign. This is not exactly 1.732. So this divide by 3. So what's the answer? Approximately 0.6. 3 times 6, 18. So here this is 5. 3 times 5, 15. 2 remaining. 23. How many 3's? 3 times 7, 21. 2 remaining. For 22, another 7. And for 10, 3. So here approximately the answer is 0.5773. Now we'll take some examples to rationalize the denominator. So in this one, what's the surd value? In the denominator, root 5. So what we do here, you multiply by that surd value, both the numerator and the denominator. Then simplify. 3 times root 5, you get 3 root 5. Over root 5 times root 5, you get 5. What about this one? Multiply this by root 3, both the numerator and the denominator. Then you can write 2 root 3 in the numerator. What are you getting for the denominator? Root 3 times root 3, you get 3. What about this one? Multiply by root 5, both the numerator and the denominator, and simplify. 7 times root 5, 7 root 5. Root 5 times root 5, you get 5. This one, here you don't need to multiply by 6 there. What's the surd value? Surd value is root 2. So you just multiplied by root 2. So what you get here? 27 root 2 divide by root 2 times root 2, 2, and 2 times 6, you get 12. Can you simplify further? I can see you can simplify these two numbers by 3. You can divide by 3. 3 times 4, 3 times 9. And you can write down the surd value as 9 root 2 over 4. What about this one? What's the surd value? Root 2. So we'll multiply both the numerator and the denominator by root 2. So you get in the numerator 8 root 2. What about the denominator? Root 2 times root 2 is 2. 2 times 3, 6. Can we see that it's divisible by 2? So divide by 2, you get 3. Divide by 2, you get 4. So what's the final answer? 4 root 2 over 3. Now we'll look at example 1 in your textbook. That's page number 10. It says simplify 3 root 5 plus 6 root 5. This can be simplified by considering root 5 to be an unknown term. So they want the algebraic method. So here I can take root 5 as x. So I can simplify this to 3x and 6x. What is 3x and 6x? You get 9x. Again, after you find out this, you can substitute the surd value. So x is root 5. So the answer is 9 root 5. When you look at example number 2, you're asked to express the entire surd as a surd. So this is the entire surd given. So what you do? You write down as a square number. 20, how can you write as a square number? I can write as 4 times 5. So then I can write separately square root of 4 and square root of 5. So what is square root of 4? I get 2. So what's the answer? 2 root 5. This one, example number 3, express the surd 4 root 5 as an entire surd. That means you have to put this outside number inside. So what you do? What's the process? When you are taking inside, you have to square it. 4 squared is 16. So here, when you are taking 4 squared inside, 16 times 5, what is 16 times 5? 5 times 6, 30, 3 remaining, 5 times 1, 5 plus 3, 8. So square root of 80 is same as 4 root 5. Now look at example number 4. It says simplify 5 root 3 and 4 root 2. Let us multiply the rational and irrational parts separately. So we'll take this one. What's the rational part? The whole number. So 5 times 4 you can multiply separately and the surd values separately. Root 3 times root 2 you can write 3 times 2. So what is 5 times 4? You get 20. 3 times 2 you get 6. So can we simplify further? No. 6 you can't write as a square number. So you have to keep the answer as 20 root 6. Now we'll look at example number 5. In this question, it says simplify 3 root 20 divide by 2 root 5. So I can write this as a fraction. So 3 root 20 divide by 2 root 5. Then what's the next step? You can write the surd value in the radical form, one radical form. So here I can write this number as 20 over 5. Now simplify, you get 3 over 2. 20 divided by 5, you get 4. So square root of 4. What is square root of 4? You get 2. So here 3 over 2 times 2. I see 2 get cancelled out. You get 3 as the answer. Now we'll look at example 6. Express 3 root 2 as a fraction with an integer in the denominator. What do you call that? Rationalize the denominator. So they want a whole number in the denominator. So what is the method? You multiply with the same surd value both the numerator and the denominator. So what you get? 3 times root 2, 3 root 2. Root 2 times root 2, you get 2. So this is the value with a whole number in the denominator. Example number 7. Rationalize the denominator of a over root b. So it's a algebraic one. What you do when you want to rationalize? You multiply both the numerator and the denominator by root value. So what you get? A times root b, a root b. Root b times root b, you get b. So here this is the rationalized form. Example 8. You are asked to simplify. Look at the surd values carefully. You get big numbers. So first thing you need to simplify inside and get the same surd form, and then you can add or subtract. So we'll first simplify inside. How you simplify? You write as a square number. 63, how can I write? 9 times 7. 7 I can't simplify. I write as it is. 28, how can I write as a square number? 4 times 7. Now try to simplify. 4, you write separately, square root of 9, square root of 7. This one as it is, and this one again write separately, square root of 4, square root of 7. Now simplify. You know square root of 9 is 3. 3 times 4, 12 root 7. You get 5 root 7 here. What about this one? Root 4 is 2. 2 times 8, 16 root 7. Now we see all surds are the same values. So you can just add or subtract. So we can do 12 minus 5, you get 7. 7 minus 16, you get minus 9. And the surd value is 7. Now we'll look at example number 9. It says simplify this one. So what we can do? So first we'll look at carefully and see how we can simplify. I can see 75, you can simplify further, but 6 you can't simplify. And also irrational numbers in the denominator. So here if I can convert these to rational forms, maybe I can simplify. First we'll see this one is division. So I can write this one as 6 and 2 7 inside the same radical form. 75 I can write as a square number, 25 times 3. What about this one? We can't simplify. So what we can do? I can rationalize the denominator. That means I multiply by root 12. Now try to simplify 2 with this, you get 3. So here you get 2 root 3. What about here? Root 25 is 5. You get 5 root 3. This one, when you multiply together, you get 3 root 12 over 12. Root 12 into root 12, you get 12. Then I can simplify 3 times 1, 3 times 4. Now 12 can we write as a square number? Yes, we can. So we'll write it down. 12 I can write 4 times 3. So what is 4 times 3 becomes 12 and 4 is there. So here again I can simplify as root 4 times root 3. So what is root 4? You get 2. So here when I simplify this, I get 2 root 3 over 4. Here same surd values I can add. 5 plus 2, I get 7. So I get 7 root 3 minus this value. Here I can see 2, you can cancel out with 2. So what's the surd value you are getting? I'm getting 7 root 3 minus root 3 over 2. So basically that means 7 minus half. So what is 7 minus half? You get 6.5 or 6.5. So how can I write 6.5? I can write 13 over 2. So here what's the answer? 13 over 2 root 3. Now we'll look at exercise 1.3 in your textbook. So you are asked to convert the following entire surds into surds. So what's the method we used? We have to write down the number with a square number. So how can we write 20? What's a square number? 4 times 5. Then you write separately and simplify. Square root of 4 is 2. You get 2 root 5. What about second one? 48. How can I write 48? What's the square number? If you can't get it at once, better to divide and see. When you divide by prime numbers, you easily see what's the square number. See how many pairs are there. This and this. 2 times 2, 4. 4 times 4, 16. So 16 is the square number. So 16 times 3. Then you can write down separately. What is square root of 16? You get 4. So we can write as 4 root 3. This one, 72. Can you remember the square number? That's 36 times 2. So what is square root of 36? You get 6. 6 root 2. 28. How can I write? 28 I can write 4 times 7. So what is square root of 4? Square root of 4 is 2. So you get 2 root 7. Now we'll look at the other questions. Root 80. What's the square number? If you can't figure it out, divide and see. So when you are dividing by 2's, how many pairs are there? You get 2 pairs of 2. 2 times 2, 4. 4 times 4, 16. So the number is 16 times 5. So what's the square root of 16? That's 4. So what's the answer? 4 root 5. 45. How can we write 45? 9 times 5. Then you write down separately. Square root of 9 is 3. So this is 3 root 5. What about 75? What's the square number? 25 times 3. So when you write down separately, what's square root of 25 is 5. You get 5 root 3. 147. At once I can't see the square number. So I am dividing this by 7. You get 21. Again I can divide by 7. You get 3. So what's the square number? 49. So 49 times 3. I can write this as 49 times 3. Square root of 49 is 7. So you get 7 root 3. Now we'll see the second question. It says convert the following surds into entire surds. That means when there's a number in front, you have to take that one inside the surd value. So how can we do that? So here I'm trying to take this 2 inside. So when you are taking the number inside, you have to take the square term. So what's the square term of 2? 2 squared is 4. So you can write this one as 4 times 3. So what is 4 times 3? You get 12. What about the other one? 2 is outside. So when you take inside, 2 squared. So 2 squared is 4. So I'm taking this one as 4 times 5. So what is 4 times 5? You get 20. This one, 4 squared. So what is 4 squared? 16. 16 times 7. So what is 16 times 7? 7 times 6, 42. 4 remaining. 7 times 1, 7. 7 plus 4, 11. So the answer is square root of 112. What about this one? When you take 5 squared inside, you get 25. 25 times 2. What's 25 times 2? You get 50. So the answer is square root 50. This one, take 6 squared inside. What is 6 squared? 36. 36 times 11. So multiply. 36 times 11. 11 times 6, 66. 6 remaining. 11 times 3, 33 plus 6. You get 39. So 396 is the answer. Now we'll look at question number 3. It says simplify. Simplify this number. So how can we simplify? You can add or subtract when you get the same surd value. So here, what's the surd value here? Root 2. That means you can simplify. So here, there's no number, means this is like 1. So add these two. 1 plus 5, 6. 6 minus 2, you get 4. So the answer is 4 root 2. This one, what are the terms that we can add? Same surd values. This with this with this. Here, nothing means just 1. 1 plus 2, you get 3. So you get 3 root 5. 2 minus 3, you get 1. 1 root 7. Here, you don't need to write down 1. So I can rewrite this as 3 root 5 minus root 7. This one, what are the like terms? So this is root 3 and this is root 3. You can simplify these two. This with this and this with this. So 4 root 3 minus 2 root 3. So that means 4 minus 2. You get 2 root 3. These two, 5 minus 3. You get 2. So the answer is 2 root 2. This one, 3 root 5 plus 3 root 5. 3 plus 3, you get 6. 6 root 5. We can't simplify further. Now we'll look at this one. What are the like terms? Root 11, 7's here. So you can simplify separately. 6 minus 2, you get 4. So you get 4 root 11. What about root 7 values? 3 minus 5. You get minus 2. Minus 2 plus 4, you get plus 2. What about this one? What are the like terms? This and this, these 3 together. When you take root 3 values, 8 minus 2, you get 6. What about these 3 terms? Plus 7 plus 3, you get 10. 10 minus 3, you get 7. So you get 7 root 7. This one, fourth question. Rationalize the denominator of the following fractions. So what you do when you want to rationalize, you multiply both the numerator and the denominator by the same surd value. So surd value is 5, you multiply by root 5. What happens there? 2 root 5 in the numerator, you get root 5 times root 5 is 5. What about the second one? Rationalize the denominator. Multiply this by root 3, both the numerator and the denominator. So what you get here? 5 root 3. Root 3 times root 3, you get 3. This one, multiply both the numerator and the denominator by root 7. So when you do that, you get 5 root 7. Root 7 times root 7 is 7. This one, you need to multiply by root 3. You don't need to multiply by 2. So when you simplify, what you get? 12 root 3 over. Here, root 3 times root 3, 3. 3 times 2, 6. Now, you can simplify further. 6 with 1, 6 with 2. So what's the answer? You get 2 root 3. Now we'll look at these questions. You want to rationalize these denominators. So what we do? Surd value is root 2. So you multiply both the numerator and the denominator by root 2. So what you get here? 27 root 2 over root 2 times root 2, 2. 2 times 3, 6. Now you can simplify further. I can divide by 3 and get 2. 3 times 9. So what's the final answer? 9 root 2 over 2. This one I can multiply by root 5. Then what I get? 3 root 5 in the numerator. Denominator I get root 5 times root 5 is 5. 5 times 2, 10. This one, third value in the denominator is root 7. So I multiply both the numerator by root 7. So what I get? 3 root 5 times root 7. I can write as a single third value. I can take those two numbers inside. What about the denominator? Root 7 times root 7, you get 7. 7 times 2, you get 14. Now, can we simplify further? I can write this as 3 root of 7 times 5, 35 over 14. So, I can't simplify further. This one, what's the third value? Root 2. So, I can multiply both the numerator and the denominator by root 2. So, what you get? 2 root 3 times root 2 I can put inside the third form. 3 times 2 I can write as 6. What happens to the denominator? Root 2 times root 2, you get 2. 2 times 3, 6. Now I see I can simplify 2 and 6. 2 times 1, 2 times 3. So the answer is root 6 over 3. This one, what's the third value in the denominator? You get root 5. So what I can do, I can multiply both the numerator and the denominator by root 5. So what you get? 3 root 3 and root 5 I can write as root 15. What about the denominator? Root 5 times root 5? 5. 5 times 2? 10. Can I simplify further? 15 I can't write as a square number. So you have to keep like that. Now we'll take fifth question. So in the fifth question, they asked to simplify and you get multiplication. So how can we multiply? So you can multiply the rational term separately, irrational term separately. So 3 times 2, I can write 6. Then inside third value, I can write 2 times 3. So here 6 root 6 because 3 times 2, you get 6. This one, rational numbers separately. 5 times 3, 15. What's the irrational part? 11 times 7. So I can write root 77. What about the third one? I can write 3 separately and inside the third 5 times 3. So what's the answer? Root 15. So we can't simplify further because 15 I can't write as a square number. What about these 3? Now you get division. So when you get division, what you do? You write as a fraction. So I can write this one as 4 root 7 over 2 root 14. Then I can write inside one radical form, 7 over 14. Then simplify. What I'm getting? 7 times 1, 7 times 2. 2 and 4, you get 2 here. So answer is 2 square root of 1 over 2. Now I can rewrite as 2 square root of 1 is 1 and square root of 2. This is a irrational number in the denominator. So here we can rationalize it. So how can we rationalize? I can multiply by root 2 and rewrite this as 2 root 2 divide by root 2 times root 2, 2. Can you see? 2 and 2 get cancelled out and you get root 2 as the answer. Now look at the next one. Write down as a fraction form. I can write this one as this form. Then what's the next step? I can simplify the whole part like this and write the third value inside. 27 over 3. So what is 27 over 3? You get 9. What is square root of 9? You get 3. 3 times 2, you get 6. This part, you can write 48 over 5 root 3. What's the next one? You write as a single third value. 48 over 3, you get 1 over 5. So what's the answer here? 3 times 1, 3. For 18, that's 6. 16. What is square root of 16? You get 4. So here, 4 in the numerator and 5 in the denominator. Look at 6th question. You are asked to simplify. So here, first you have to write down the simplest form and then add or subtract. When you take 27, can I write 27 as a square number? Yes, I can. 9 times 3. This one I can't. 7 I can't write. What about 28? 28, what's the square number? 4 times 7. Now try to simplify. I can write this one separately. Square root of 9, square root of 3. I can write this number as it is. What about this one? I can write as square root of 4 and square root of 7. Now simplify. What's square root of 9? You get 3. 3 times 2, 6. So you get 6 root 3. What about this one? You can write as it is. This part again you can simplify. What's square root of 4? 2. 2 times 3, 6. You get 6 root 7. Now can we simplify further? We can simplify same third value. So these 2 and these 2. So 6 minus 3, you get 3. 4 plus 6, you get 10. That's the answer. What about the next one? You have to write again these numbers as a square number. 63, how can I write? If you can't sure with that, you can do the division and see. Divide by 3, you get 21. Divide by 3, you get 7. So what's the square number? 9 times 7. This one you can't simplify. 27 again you can write as 9 times 3. This one you have to write as it is. Now try to simplify. Square root of 9 and square root of 7. This one, same thing. This one I can write square root of 9, square root of 3, and this one, same. Now try to simplify. What is square root of 9? 3. 3 times 3, 9. Then this one. Square root of 9 is 3. 3 times 3, 9. Now simplify these two terms together and these two together. 9 minus 2, you get 7. 9 plus 3, you get 12. So you get 7 root 7 plus 12 root 3. Now we'll look at part C. Here also you are asked to simplify. So we'll do separately. 128 can we write as a square number? See, we'll divide and see. Here we know 64 is a square number. So 64 times 2. What about 50? We know that that's 25 times 2. What about 162? We can check. Divide by 2. 81 is a square number. 81 times 2. What's this one? That's in the denominator you get an irrational number. So it's better to rationalize it. So I'll do it straight away. I can multiply both the numerator and the denominator by root 2. Now we'll try to simplify. 64 is a square number. When you take square root, you get 8. 8 times 2, 16. So you get 16 root 2. What's the square root of 25? That's 5. 5 times 3, 15. So you get 15 root 2. What about the other number? Square root of 81 is 9. 9 times 2, 18. This one, when you rationalize this, what you get? I get 4 root 2 divided by root 2 times root 2 is 2. I can see 2 and 4 get cancelled out and you get 2 root 2. Now we'll try to simplify this. All surd values with root 2. So I can just add and subtract. 16 minus 15, you get 1. 1 plus 18, you get 19. 19 plus 2, you get 21 root 2. This one, 99. What's the square number for 99? We know that's 9 times 11. So I can write 9 times 11 for 99. What about 44? I can write 4 times 11. And this one I can rationalize. I can multiply both the numerator and the denominator by root 11. Then you can separately take the square root. What's square root of 9? You get 3. So the answer is 3 root 11. What about this one? Square root of 4 is 2. 2 times 2, 4. You get 4 root 11. What about this one? You get 110 square root of 11 over root 11 into root 11. You get 11. So I can see this one get cancelled out with this and I get 10. Now look at carefully, all same surd form. I can just add and subtract. 3 minus 4, I get minus 1. Minus 1 plus 10, I get 9. So the answer is 9 root 11. What about this one? Root 20 over 2 minus root 5. So here also we have to write root 20 in terms of square number. How can I write? 4 times 5. What about this one? I can write as it is. Then simplify. I get square root of 4 is 2 and 2 root 5 divided by 2 minus root 5. Here root 2 and 2 get cancelled out. You get root 5 minus root 5. What is root 5 minus root 5? You get 0. In this lesson, I covered all examples and exercises related to real numbers and surds. So here you know what are real numbers and how to simplify surd values.